Hello and welcome to another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 10, Lesson 5 on applications of scientific notation. Now we've done some applications with scientific notation throughout this unit, but today we're just going to be concentrating on that. Make sure to have your calculators handy. We're going to be using them. When necessary, we may even put them into scientific notation mode. All right, so let's jump right into it and start playing around with problems that involve very large and very small numbers. Now remember, that's what scientific notation is all about. Scientific notation is most useful when we're working with very large or very small quantities. And again, when I'm talking about very small quantities, I'm not talking about the number 1 or the number 2. I'm not saying, hey, I got two apples or $2 in my wallet, so I have a very small amount of money. No, I'm talking about like, oh, the size of a bacteria is 0.000045 meters or something like that. That's what we're talking about with very, very small. Very large is easier to think about than very small often. So let's start with a problem involving very large numbers. Exercise number 1. The equator along the Earth is roughly 2.49 times 10 to the 4th miles long. The equator around the Sun, however, is 2.72 times 10 to the 6th miles long. To the nearest integer, determine how many times larger the equator of the Sun is than that of the Earth's. Show your calculation. Now, before we get into this, right, you might wonder, should I put my calculator in scientific mode or not? I would actually not have it in scientific mode unless you absolutely need to have it. Now in this particular problem, we're just trying to find out how many times larger the equator of the Sun is than the equator of the Earth, and we want it to the nearest, to the nearest integer. So is it, 20 times larger, 32 times larger, 57 times larger? Well, see if you can figure that out by using your calculator, not in scientific notation, but perhaps, using the scientific notation to put these numbers in. Pause the video now and see what you can find. All right, well, whenever we're trying to find out how many times greater one number is than the other, we need to use division. Specifically, what I need to do is I need to take 2.72 times 10 to the 6th miles for the Sun, divided by 2.49 times 10 to the 4th miles for the Earth. All right, now this is where I'm going to use my calculator. Okay, now remember, I want to put those numbers in parentheses when I've got division going on. So I've got 2.72 times 10 to the 6th. All right, that's the number of miles in the Sun, or the equator of the Sun, divided by 2.49 times 10 to the 4th miles of the equator of the Earth. I hit enter and I get an answer that is in non-scientific notation mode, which is good. So I can say that the Sun is 109 times greater around its equator than the Earth is. That's a lot, right? I mean, the Sun is large, so is the Earth. But the Sun's equator is 109 times larger than that of the Earth. Now again, we could do this with these numbers not written in scientific notation, but they'd be ugly. I'd have to be like, yeah, the equator of the Sun is 2,720,000 miles, and the equator of the Earth is 24,900 miles, right? Much easier to put those distances in scientific notation, and then easy enough to do the division. All right, let's keep going, working with more numbers that are very large and very small. Exercise number 2. In the year 2014, not that long ago, Americans ate a total of 6.84 times 10 to the 10th pounds of meat. That doesn't even include fish. In that year, the population of America was 3.18 times 10 to the 8th people. What was the unit rate of meat eaten per person round to the nearest pound per person? In other words, I want to know in 2014, if everybody ate the same amount of meat, how many pounds per person would they have eaten? Pause the video now and see if you can figure this out. Again, notice this problem doesn't ask for the answer in scientific notation. So there's really no reason why I'd want to put my calculator into science mode right now. Now, all I'm doing here is a ratio, right? I'm just doing a ratio that the likes of which you've been doing for years now. The big difference is the numbers in the ratio, the numbers in the fraction are really big numbers, right? So what do? Well, I take 6.84 times 10 to the 10th pounds. That's how much meat is eaten. That is a huge amount of meat. Divided by 3.18 times 10 to the 8th people. And that's a lot of people. All right, and that's going to give me the pounds per person, right? So let's take a look. Again, with the parentheses, always with division, 6.84 times 10 to the 10th divided by 3.18 times 10 to the 8th. And that gives us a nice, just, normal looking number. I want to round to the nearest pound, so that's 215 pounds per person. 250 pounds of meat per person in the United States. Could be beef, pork, right, poultry, just apparently not fish. That's a lot. Now, I mean, it's a lot of meat, right? I mean, 200 pounds, but that's over the span of a year. So it's a little bit less than a pound per day consumed by people. Still a lot of meat. I think we need to cut down on that. Maybe a little bit, maybe not. All right, let's keep going. Let's take a look at exercise number 3. The shape of planet Earth is well modeled by a sphere whose radius is 2.09 times 10 to the 7th feet in length. Given that the volume of a sphere is V equals 4/3 pi r cubed, I think I remember that from our last unit, find the volume of planet Earth in cubic feet. Express your answer in scientific notation with 2 decimal place accuracy. Okay, so now this is one where it may be good to have my calculator in scientific mode, all right? So let's review how to do that. I want my answer in scientific notation mode, so I'm going to go up to mode. I'm going to go down to scientific, hit enter. I'm going to quit out of my mode button. Now I'm going to put my calculator away for just a moment, all right? Now make sure your calculator's in scientific notation mode or science mode, okay? Now what I'd like you to do is try to use this formula along with the radius to figure out how many cubic feet are in the Earth. Pause the video now and see if you can use the formula correctly. All right, awesome. Let's do it. So we know the volume of a sphere is 4/3 times the number pi times the radius cubed. Now our radius in this case, 4/3, let's try that again, is 2.09 times 10 to the 7th. But then I'm cubing it, okay? So let's see what we get when we plug all of this into our calculator. All right, we got 4 divided by 3 times pi times parentheses 2.09 times 10 to the 7th, all raised to the 3rd. Whoops, that didn't quite happen. Let's try that again. I didn't quite get the caret button there. All raised to the 3rd. And what do I get? Wow. I get 3.82. I just want 2 decimal places of accuracy. 3.82 times 10 to the 22nd cubic feet. Wow. Now, the Earth is big, right? I mean, the Earth is really big, but a cubic foot's not small, right? That's a cube that's a foot by a foot by a foot, right? And there are 3.82 times 10 to the 22nd cubic feet contained in the Earth. Huge, huge number, right? Huge number. All right, let's keep going. Let's take a look at number 4. A teaspoon of water weighs 5 grams. A single molecule of water weighs 2.98 times 10 to the negative 23rd grams. How many molecules of water are there in a single teaspoon? Express your answer in scientific notation with 2 decimal places of accuracy. All right, well, cool. We already have our calculator in scientific notation. Now again, review. A teaspoon. Imagine a teaspoon. It's not the biggest thing, right? It's one of the smallest measuring devices you probably have in your kitchen. A teaspoon of water weighs 5 grams, and every single H2O molecule weighs 2.98 times 10 to the negative 23rd grams. Very, very small. Given those 2 numbers, I'd like you to figure out how many molecules of water there are in a single teaspoon. And it's going to be a large amount. Pause the video now and see if you can figure out how to do this. Well, we want to take our weight of 5 grams and we want to divide it by how many grams per molecule we have. So I'm going to have 5 grams divided by 2.98 times 10 to the minus 23rd grams per molecule. All right, let's see what this gives us. Clear this out. 5 divided by, get my parentheses going here, 2.98 times 10 to the negative 23rd. I think we got it all there. And that is 1, and again we want 2 decimal places of accuracy, 1.68 times 10 to the 23rd molecules. 1.68 times 10 to the 23rd molecules of H2O in a teaspoon. Now, you know, kind of cool, just as a little perspective, that's a huge number of molecules, right? A single molecule of water, right? And there are 1.68 times 10 to the 23rd molecules in a teaspoon of water. By the way, if you go back just one slide, take a look at this. There are 3.82 times 10 to the 22nd, notice that, 10 to the 22nd cubic feet in the Earth. There's more molecules of water in a teaspoon of water, 10 to the 23rd, than there are cubic feet in the Earth. And that's, of course, because a molecule of water is exceptionally, exceptionally small. Isn't that amazing? Talk about a big number. That's a big number. That's a lot of molecules of water in a single teaspoon. All right. Now, we've got one final problem to look at. But before we do that, I want to review a very simple thing about finding percentages of a whole. Let's take a look at exercise number 5. Find each of the following using a product. Show your product and final answer. Now, you should already know how to do this, so I'd like you to pause the video now and see if you can find 5% of 300, 12% of 50, and 1% of 270 by simply just doing a product. See if you can remember how to do that and see what you get. All right, well, to find 5% of 300, right, means that we're multiplying 300 by 5/100ths or by 0.05. So to find 5% of 300, we multiply 300 by 0.05. And that's, of course, simple enough to do. We could probably even do it without our calculator, but, you know, we got the calculator going, so why not? And oh, hey, we're in scientific notation mode. I'm gonna take it out of that mode because I don't actually want this answer in scientific notation, but we've got 0.05 times 300. We might put our calculator back in scientific notation mode in a moment, but we get 15, right? Likewise, to find 12% of 50, we're gonna multiply 0.12 times 50, and let's see what we get there. 0.12 times 50 gives me 6. Simple. And the most important one of the three, to find 1% of 270, we're going to multiply 270 by 0.01. And this should come as no surprise. This gives me 2.7. All right. So I just wanted to review really quick how we find a percentage of a given number by doing a product. And all we're going to be doing is finding 1% of a given number in a little while. That's why that one's so important. So let's, in our final exercise with scientific notation, let's look at a very profound question that hopefully you've all thought about, right? Final, quite profound question involving scientific notation. Let's take a look at exercise number 6. Is there other intelligent life in the universe? Okay, let's back out of it just for a second. Now, right, life. We all know what life is. Plants, animals, bacteria, whatever, right? Then there's intelligent life. Now, however you want to define that, intelligent life is typically thought of as being kind of life like humans, right? Not like dogs or cats or birds or amoebas or anything like that, but like creatures that are intelligent enough to maybe have written language, maybe have invented machines, maybe they mold the environment for their own uses, right? We are the only intelligent life in theory on Earth that has that capability, okay? And the question is, right, is there other intelligent life out there? How likely is that? Is that, you know, in theory, we've never been visited by other intelligent life. I don't know, maybe we have, maybe we haven't. Certainly it's happened plenty in Hollywood. But my point is, let's run the math. Let's figure out, you know, could there be other intelligent life out there? Let's take a look at that in exercise number 6. Let's revisit that now. Is there other intelligent life in the universe? Let's start with just the Milky Way galaxy, the galaxy we live in, not the solar system, the galaxy. The Milky Way galaxy contains up to 4 times 10 to the 11th stars. Let's back out of that for a second. 4 times 10 to the 11th, I just want to kind of give you a sense for that. It's written in scientific notation, but again, just to really kind of get a feeling for that, One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes, that is 400 billion. All right, our galaxy alone, the Great Milky Way, has around 400 billion stars in it. 400 billion stars, just like our own sun. I mean, they're not all just like the sun, but whatever. All right, let's take a look at letter A. If only 1% of all those stars, if only 1% of the 400 billion stars had planets, how many stars would have planets? Show the calculation. Express your answer in scientific notation. So again, I just want to be very clear, right? I'm saying if you took every 100 stars, only one of them would have any planets at all. You know, any Jupiter, Mercury, Earth, Mars, whatever. Only 1 in every 100 of these stars would have a planet. How many stars would have planets? Well, to do that, right, we would just take 0.01 and we would multiply it by 4 times 10 to the 11th. All right, well, let's do that. All right, now I think I'm going to actually put my calculator back in scientific notation mode just for the time being. You don't have to, but it doesn't hurt. And let me do 0.01 times 4 times 10 to the 11th. So just 1%, we're just going to assume, and look at that. It's 4 times 10 to the 9th. Now let's talk about why it went from 4 times 10 to the 11th to 4 times 10 to the 9th. That should be no great surprise to us because 0.01 is 10 to the minus 2. So literally, we just have 10 to the minus 2 times 10 to the 11th, then it goes down to 10 to the 9th. So again, real conservative, right? There are 400 billion stars out there, and we're saying just 1 in every 100 stars has a planet, and therefore there would be 4 times 10 to the 9th stars that have at least one planet. Now, I know I just said put it in scientific notation, but I'm actually going to write this out in non-scientific notation. This actually happens to be 4 billion. So again, like Under my very conservative assumption that only 1 in every 100 stars even has a planet, there would still be 4 billion stars that have planets. 4 billion stars that have planets. That doesn't mean they have life, much less intelligent life. Now let's take a look at letter B. If only 1% of all the stars that had planets contained one planet that could support life, known as planets in the Goldilocks zone, how many planets could support life? Show the calculation, express your answer in scientific notation. All right. Now, by the way, this is one of the greatest terms in all of astronomy, Goldilocks zone, right? You know the tale of Goldilocks, right? The girl who goes into the house with the bears who are eating porridge, and like some porridge was too hot, some porridge was too cold, and some porridge was just right. Well, the idea of a Goldilocks zone is that, there are only certain zones around stars that are just perfect for life to form. Because quite frankly, if you get too close to a star, it's too hot. And if you get too far away from a star, it's too cold. So if you're just in the right spot, you're in the Goldilocks zone. So let's just say of these 4 billion, right, only 1% of them even has a planet in the Goldilocks zone. Well, that would now be 0.01 times 4 times 10 to the 9th. Remember, that's how many of our stars even had planets. Let's just say 1 in every 100 has a planet in the Goldilocks zone. And this should be no surprise when we do 0.01 times 4 times 10 to the 9th, we now have 4 times 10 to the 7th. Now, what is 4 times 10 to the 7th? That's actually 40 million. Now, again, I'm not claiming that there are 40 million stars out there that have planets that have life on them. I'm saying that there were maybe 40 million stars out there that have planets that could develop life. That they're in that same kind of region that the Earth is, not too hot, not too cold. They're in the Goldilocks zone. 40 million. 40 million stars, right, that could have planets that support life. But let's keep going. Letter C. Now let's say that just 1% of the planets you found in B actually did support life of any kind, How many planets in the Milky Way would support life? Show the calculation, express your answer in scientific notation and standard decimal form. All right? Now again, we're talking about any life. We're talking about like primordial sludge, you know what I mean? Like algae, bacteria, amoebas, anything. Let's just say 1% of these 40 million have life, right? So that's going to be 0.01 times 4 times 10 to the 7th. I think you've seen the pattern enough now to know that that would then be 4 times 10 to the 5th, which would be 400,000. All right. So, think about this. We've said, look, there are 400 billion stars, but only 1 in 100 have got planets, right? So then that's, 4 billion stars that maybe have planets, right? But only 1 in 100 of those have planets that could support life. So that's 40 million stars have planets that support life. And of that 40 million, maybe 400,000 actually have life on it. All by itself, that's pretty profound, right? That there could be 400,000 stars out there in our galaxy alone, and there are many galaxies, 400,000 stars out there that could have life. And now let's say only 1 in every 100 of these planets that have life have intelligent life. And that's the last part, right? Letter D. Now let's say that just 1% of all the planets that had life on it include at least one life form that is intelligent. How many planets would have intelligent life on them? Show the calculation, express your answer in scientific notation and standard decimal form. So again, 400,000 planets have life on them. How many of those have intelligent life? Let's just assume it's 1% times 4 times 10 to the 5th. That would be 4 times 10 to the 3rd. That would be it in scientific notation. And that would be 4,000 planets. using what's called conservative estimates. 1%, 1 out of every 100, right? 1 out of every 100 stars has a planet. 1 out of every 100 of those have a planet that is in the Goldilocks zone. 1 out of every 100 of those then has actual life on it, and 1 out of every 100 of those has intelligent life, and that still means that up to 4,000 stars would have intelligent life. Life forms like us that have written language, machines, computers, things like that, right? The ability to manipulate fire and the elements and whatnot. 4,000 instances of intelligent life. And by the way, that's just our galaxy. Believe it or not, right, even though this would be a lot of planets, astronomers believe that there are around 100 billion galaxies, 100 billion Milky Ways in the entire universe. And apparently Thanos rules them all. Maybe not. But the point is, right, if you took that 4,000 and you multiplied it by this number, right, there'd be 4 times 10 to the 14th planets that have intelligent life in the universe, all right? This is a million. This is a billion. This is a trillion. 400 trillion planets in our universe that have life, and that's if we're being very conservative with that 1 out of 100 in each stage. Isn't that amazing? Right? So if you have any doubt whether or not there's extraterrestrial life out there, this is a pretty convincing argument that in all likelihood there is. All right, let's wrap this up. Enough with profound questions about the universe and extraterrestrial life, right? In this particular lesson, we looked at calculations that we could do with numbers written in scientific notation. And in each case, we were always dealing with quantities that were very large, or like in the case of that, like the size of a molecule of water, very, very small, all right? And it's interesting because when we deal with numbers that are very, very large, we can get, or very, very small, we can get some surprising results like what we saw with that examination of whether or not there's other intelligent life in the universe. Again, I don't know whether there's not or whether there is or not. I'm not even sure there's intelligent life on this earth. But one thing I do know is that there are so many stars and so many galaxies in the universe that in all likelihood, there's not just some extraterrestrial life out there, there's a lot. Anyway, we've got one more unit in Math 8. This is the last lesson of Unit 10. One more unit to go, and then we are done with this course. I just want to thank you for joining me for another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.